completely new topic, and the topic is extremal graph theory, and we start with sparse extremal graph theory. So very, very broadly, sparse graph theory is about graphs that have roughly a linear number of edges, linear in the number of vertices, okay? And dense graph theory is about graphs that have roughly quadratically many edges, as many as they can have by the order of things. And of course, when I say linearly or quadratically many, that's completely undefined for a single graph. It's defined for classes of graphs, but planar graphs, for example, are sparse graphs, right? And complete graphs, complete bipartite graphs, and so on are dense graphs. So we start with an overview of the bounds on the edges, edge numbers, that will force a KR minor or topological minor on a graph. And before that, just a reminder of how many edges we need to force a KR subgraph. That's Turán's theorem, right? We need quadratically many edges to force a KR subgraph. So the average degree, let me express everything in terms of average degree here. The average degree that we need to force a KR subgraph is some constant times n, right? And this constant is this Turán number, r minus 2 divided by r minus 1. Right, so that's how many edges will force a KR subgraph, and no fewer edges will achieve that for an arbitrary graph G. Okay, we need an average degree of constant times n to get a KR subgraph, and the constant is r minus 2 divided by r minus 1. Okay, so how about an arbitrary subgraph? Not just a KR, but any graph H. Well, there we had this corollary to the Erdös-Stone theorem. The Erdös-Stone theorem will be proved later in this course. We saw it stated and a corollary derived from it, and the corollary said that basically you get exactly the same as you do for KR, except you have to replace R with the chromatic number of the graph that you're forbidding. So once more, how many edges will force an arbitrary graph H as a subgraph, or which average degree of G forces that? The answer is the same as before, some constant times n, and this let me express it by saying some constant depending on H plus a little bit, plus epsilon, times n, where this constant depending on H is what it was for KR, but now adapted to arbitrary H, namely the chromatic number of H minus 2 divided by the chromatic number of H minus 1. That's what you get for the case of H equals KR, but it's quite amazing that this works for an arbitrary graph H, and that the chromatic number somehow suddenly enters this field of investigation at all. Chromatic number is not normally something that you meet every day when you study extremal graphs, and here suddenly it occurs in a very prominent way. Okay, so let's look at two special cases, a special and an even more special case. The special case is when H is bipartite. So when H is bipartite, what does this constant say? It says chromatic number of H minus 2 divided by something. Chromatic number of H minus 2 is already 0. So the corollary to the Erdös-Stone theorem says that if you have 0 plus a little bit, in brackets, times n as an average degree, then you get this bipartite graph H as a subgraph. So epsilon times n as an average degree suffices to force a bipartite graph H. And this is true for any epsilon as small as you like, provided n is big enough. Right? You choose the epsilon, tiny, 1/1,000,000. And then if you make n large enough, then all graphs with average degree n/1,000,000 will contain your favorite bipartite graph H. Okay, and this can be improved on, which is not hard. And here's an upper bound for KRR. This bipartite graph with equal vertex classes, and it turns out that you only need constant times n squared, n to the 2 minus 1 over r edges, right? So rather than n squared, we get n to the power of 2 minus 1 over r as an upper bound on the edges that you need to force that. So that's a little better than what we had before as just by plugging in h into the Erdös-Stone corollary. This is an exercise. Maybe you get it on your sheet. So by the way, maybe I ought to say that this corollary to the Erdös-Stone theorem took 20 years to be noticed. The Erdös-Stone theorem was there in, I don't know, published in 1946 or something. And it was only in 1966, that Miki Shimonovich and Erdős together published a paper noticing this corollary, which is really the main statement that we take home from the Erdös-Stone theorem these days. Okay, so this is what you get for bipartite graphs. There's also a lower bound, which says that, which is also essentially constant times n to the power of, and then 2 minus a little more, 2 minus 2 over r plus 1. And you get that by random graphs, and that is not going to be an exercise now. Okay, so those are easy improvements on the direct upper bound that we get from the Erdös-Stone corollary. And what I want to mention now is that for trees, there's a stunning, very, very clean statement that purports to give exactly the right number that you need for trees. And that is a conjecture, the Erdös-Sós conjecture, due to Paul Erdős and Vera Sós. They're both dead now. Vera Sós just died this year. She was a grand old lady of combinatorics and number theory in Budapest. And she just died this spring. So their conjecture says that if your average degree is bigger than k minus 1, then you get, as a subgraph, any tree on k edges. Right? So, once more, the Erdős-Sós conjecture says that for every k, for every tree T with k edges, so k plus 1 vertices, k edges, and for every graph G, the following holds, that if the average degree of G is bigger than k minus 1, then this particular tree T will be found in G as a subgraph. Okay, so the proof of that is a never-ending story. It's quite amazing that apparently we got quite close to a proof of this, at least for large n, for large graphs. But for every k, this was announced in 2009, to the best of my knowledge, by 4 people. Itai, Komlosh, Semeredi, and Shimonovitz. And these gentlemen are all about 80 now. So every time I bring out a new edition of my book, I ask them, any news on this? And is it going to appear like yesterday or something? And so I wrote the same letter. I copied my last inquiry to Shimonovitz. I wrote him yesterday, and he replied instantly, well, as you're writing, I'm just working on the proof. And it's not clear whether it's going to be 2 or 3 or 4 papers, or maybe 5, but I'm working on it. So, yeah, let's hope that they do end up publishing this, or else it may be lost. So, proofs do get rather long, and these days in extremal graph theory. And the reason for that is that there's a whole machinery involving the regularity lemma that does things sort of approximately, and then there's another whole machinery that ties up the approximate things and nails them down to become precise statements. And those two together are quite enormous and make for very, very long papers. So maybe I'll give you an update towards the end of this course. Maybe you come back in 10 years' time, and then I'll give you an update. Who knows? Anyway, so that's the Erdös-Sós conjecture. And now let's look at minors. So this is the sparse extremal graph theory that I spoke about earlier. What average degree do we need to force a KR minor? Well, you know that already. You need constant times R root log R as an average degree. And this constant is independent of R. Same constant, like 27.5, times R root log R, average degree will force a KR minor in any graph. And that is about tight. This, by order of magnitude, this is a tight bound. And I'm not going to revisit that in this course. For topological minors, right, subdivisions of KR, we have an additional problem in that we need vertices that can serve as branch vertices. They have to have degree at least R minus 1, and then we need independent paths between them. It's a little more difficult than arbitrary minors, and indeed you do need more edges. So once more, there's a constant, a different constant independent of R, such that this constant times R squared as an average degree forces a TKR in your graph, a KR topological minor. Okay, so that's an overview of things that you probably know already. And what I want to prove first today is a rather strange looking and counterintuitive statement which tells us something about girth forcing, large girth forcing a complete minor. Now, what does girth have to do with forcing substructures? When your graph has large girth, then locally it looks like a tree. So you start at any vertex, you look at its neighbors, you look at their neighbors, you look at their neighbors, and so on. And you can do that for a while, and you will never see the same vertex from two different vertices that you have already. So when you take all the neighbors, you will not generate a cycle, because that cycle will be short. Okay, so if you assume large girth, then locally, no matter where you start, at any vertex, when you grow the subgraph of the vertices you can see by traveling a distance of no more than some d, say, then you get to something like 2 to the d many vertices that are all distinct, and the graph you're inducing is going to be a tree. So there's this theorem of Erdös that tells you that you can have graphs of large chromatic number and large girth at the same time. Right? So if your chromatic number is large, then you have a graph of large, a subgraph of large min degree, and inside that subgraph, you can find a kr minor if that min degree is large enough. So there exist graphs of girth as large as you like that still have a kr minor. Yeah. So how can a graph that starts locally like this have a kr minor? Well, either it contains lots more vertices, or else if it doesn't, and it needn't, it can have a kr minor because it's possible to pair up the vertices that you get to the leaves of this tree in such a way as to not generate shorter cycles than are necessary here. So you wouldn't join this vertex to that vertex or to this vertex, but it's possible to pair them all up in such a way that the entire graph also gets large degree, even if your degree is bigger and you start growing this tree in the graph of large girth, you still get a tree, and then you can add all these edges to wrap it up to give the entire graph min degree, whatever you wanted, in such a way that you get a kr minor. So that's quite something to state, and it's not easy to come up with a precise rule of how to draw these edges. And the theorem that I want to show you tells us that not only is large girth not an insuperable obstruction to getting a kr minor, it is in fact a reason for getting a kr minor. So that is really something. So you have the theorem up there, and it says that if your min degree is at least 3, it has to be. If it's 2, then you can have very long paths, and nothing like a complete minor will ever come of making these longer. So if your min degree is at least 3, and your girth is large enough, you have a kr minor. So for every r, every graph of girth at least function of r will have a kr minor as long as its min degree is at least 3. If you assume that the min degree is a little bigger, then you don't have to make the girth so large, but basically it works for 3 as well. So large girth doesn't only not get in the way of giving you a kr minor, it actually creates one. Okay, so we'll prove that by way of a lemma, which looks a little more technical, but contains the gist of what the theorem says. And it says that if your graph of min degree at least d, which is at least 3, has girth at least 8k plus 3, then it has a minor whose min degree is at least d times d minus 1 to the k. So that looks technical. What is d times d minus 1 to the k? Well, that's, d is at least 3, so this d minus 1 is at least 2. So that's the 2 to the k that you get as the growth of these trees in graphs of girth at least 2k. You need average degree, or min degree is even better, at least constant times r root log r. So you can wish for your r, then you know how many edges you need, what an average degree you need, namely constant times r root log r. And then you make k big enough that 2 to the k is at least that much. And you say, this k, that's big enough to ensure that 2 to the k, and in particular the min degree of this h that you find here, is bigger than this constant times r times root log r. This k I take as my girth. Or more precisely, this lemma says what exactly you need to take as the girth, and that is not k itself, but 8k plus 3. Right, so it's clear that this lemma implies the theorem, that there exists such a function that assigns to R some girth, so that every graph of at least that girth contains a kr minor, has a kr minor if its min degree is at least 3. It implies that easily, just by making the girth large enough, by making this function grow fast enough. So let's prove that lemma. The idea is to grow the branch sets of our desired minor h by planting trees in G rooted at vertices far enough but not too far enough. So we take a set X of vertices in G, which we make as large as we can, so that between any two vertices in X, little x here, little xy, also in big X, we have more than 2k distance. Okay? That is where we plant our trees. We find a set X of vertices in G, pairwise farther apart than 2k, but we take a maximal such set. And then we start growing little trees around these vertices. And these trees are going to be the sets that we shall contract in order to get H. We want H to have large min degree. Okay? So we'll contract these trees later to form the nodes or vertices of H, and we want H to have large min degree. So how can we have a large min degree? Well, we want each yellow blob, each tree, to send edges to many other yellow blobs. How can we ensure that? By ensuring that it has lots of leaves. Every tree has lots of leaves. And to give it lots of leaves, we must make it big enough. And every leaf sends out many edges, but not to the same other tree. So yellow, H, will have large min degree, which is what we want. If we can make these trees big enough that they have many leaves, ensure that these leaves send out, well, the min degree of G is at least 3. So every vertex here, every leaf, sends out 2 edges to somewhere. And we want this somewhere to be to many different other trees. And somehow the definition of X will help us ensure this. Okay, so let's see exactly how this works. Let's grow these trees step by step. As follows. So here's our big graph G. We take a little x. No, sorry. In each step, we start with little trees consisting only of the singletons x. So tx op 0 is just the vertex x. Then tx op I is obtained from tx I minus 1 as follows. We suppose we have grown our trees a little bit. And now let's look at a vertex adjacent to the current version of tx, so tx I minus 1. If a vertex is adjacent to it, well, let's add it to that tx. Might this x not be unique? Could it be that this vertex is also adjacent to a vertex in the other, a leaf in another ty? Well, not for the start, because this x and this y here have distance bigger than 2k. So as long as I is not bigger than k, every vertex that has a neighbor in any of the trees grown so far will have a neighbor only in that tree. Right? Otherwise, if it had a neighbor in this tx and another neighbor in ty, we'd have a short path from x to y, one of length at most 2k, which we don't. Okay, so we join every vertex that are adjacent to something in the existing trees to that unique tree. And we keep doing that until we have grown tx up I. after that, it can happen that a new vertex is adjacent to two trees. I mentioned this implicitly before, but if it's adjacent to a vertex in one of our trees, it must be a leaf, because if it was adjacent to another vertex, it would have been added to that other vertex at the previous step or an earlier step, right? So now after step k, it can happen that a vertex sees more than one tree because the path that we get from between the two roots of those trees now is no longer at most 2k long because this now is bigger than k each of these. Right? We're talking about I bigger than k now. Never mind, if we find such a vertex adjacent to more than one tree, we just add it to one of them. This one, say, and not the other. So we add some more vertices. In this way until we've covered all the vertices of G. And when is that going to happen? Well, we can't, it will happen when I is at most 2k, right? If we hadn't reached every vertex, by the time we're allowed to travel a distance of 2k from the root of a tree, then that vertex that we've missed has distance bigger than 2k from every root. But then it should have been added to x, because x was maximal with the property that its elements have pairwise distance bigger than 2k. So as soon as we're allowed distances of up to k, we know that we have covered all the vertices of V, of G. Okay, so the growth of our trees has an early phase, I up to k, where they grow uniquely without us making any choices, and then another phase where I is between k and 2k, where we have to choose where we add a vertex, possibly have to choose where we add a vertex, but that's fine. So let's make some observations about these trees. And the first observation is that these trees are induced. And why are they induced? So chordless, right? You can't have a chord between any vertices of the same tree. And the reason for that is that if you did, then you'd have a short cycle. So that from here to there is distance at most 2k. From here to there is distance at most 2k, so you have 4k plus 1, and the girth is at least 8k plus 3. Right, so we don't have that. The Tx are induced, so Tx are the fully grown trees. And the next observation is that when we look at two of these trees, say little x and little y, there's at most one edge between them. And the reason is similar. If we had two edges between the same pair of trees, then again we'd have a short cycle. So this has distance at most 2k to the root. This has distance at most 2k to the root. So the distance of this is at most 4k. Here the distance of this is at most 4k. So we have 8k plus 2 length of our cycle. But fortunately, but of course by design, the assumption is that the girth is 8k plus 3 at least. So we don't have that either. Between any two distinct trees, there's at most one edge. Okay. And now we want each tree to send many edges to other trees, or edges to many other trees. So let's just see how many vertices, how many edges does a single tree send out. Well, a little vertex in the initial tree, txk, doesn't send any edges out. So for clarity, let's put it inside that tree. So this vertex here doesn't send an edge to that tree. Why not? Because if it did, then this vertex would have been added to this tree at the step when these vertices were considered. Because this vertex, as I have drawn it, doesn't live in that tree yet. Can it live in that tree? Well, could it be down here? No, that would give us a short path between this little x and this little z in big X. Or put another way, this vertex would have had two options of being added here and being added there, but we know that early, while I is at most k, vertices don't have two options. Okay, so every vertex in up to tk, tx, k minus 1 has all its neighbors, its g neighbors, in tx itself. And these neighbors that it has in tx itself, of course, are the neighbors that we see. Right? Tx doesn't have chords, as we observed earlier. Okay, so those edges, those vertices of tx don't send edges out. How about the other edges, the other vertices? Well, because the txi's have all their neighbors inside tx, we know how many leaves txk has, namely the greatest possible number of or the number of leaves that our growth rate guarantees. So we have degree at least d, little d, which is at least 3 at x. And then at every vertex, we have d minus 1 new neighbors. And we keep having those. So if we count the leaves of txk, well, what do we get? We get d times d minus 1 times d minus 1 times d minus 1 times d minus 1 up to level k. So that's d times d minus 1 to the k minus 1. We know that Tx has at least that many leaves. Let me write this down. Txk has at least d times d minus 1 to the k minus 1 leaves. Well, but then so does Tx itself, because from every leaf, you can just travel to, from every leaf of Tx, you can travel to some leaf of, from every leaf of Txk, you can travel out to a leaf of Tx, unless it is itself a leaf of Tx like this one already. So you just find one, so we know that Tx itself also has this many leaves. Okay, so that's good news. We know how many leaves we have here, and every leaf has one neighbor in Tx. It has no neighbors in Tx other than that, because Tx doesn't have any chords. So it sends out how many edges? Well, d, the guaranteed min degree, minus 1 at least. So at least 2 if d is 3. So the entire tree, Tx, sends out at least this many vertices times d minus 1 edges. So we get sends out at least d times d minus 1 to the k edges. And we know that these edges go to distinct other trees. Right? Tx, every Tx, for every x and big X, sends out that many edges to other trees. Okay, and this, therefore, is the, since these other trees are distinct, this is a lower bound for the degree of every vertex of H, right? And that is the lower bound we wanted to prove. So here, we wanted to find a minor H in G whose min degree is at least this, d times d minus 1 to the k. That ends the proof of the lemma. Questions? No, it was easy. Yeah. Okay. So that was Thomason's theorem. You can, there's a theorem something like 15 years later, proved by Marder. Marder was one of the eminent early graph theorists in Germany. There were three of them. Harlin, who was in Hamburg, Marder, who was in Hanover, and Jung, who was in Berlin. They were all those three were students of Klaus Wagner. Klaus Wagner was sort of one of two really early graph theorists in Germany. He was in Cologne, and the other early one was in East Germany, Horst Sachs, and he set up his own school over there, and there was a little bit of exchange between the two, but obviously not very much. Okay, so Marder proved that Thomasson's theorem has an analog for topological KR minors, and it's the same statement, right? So we need to ensure, obviously, that we have vertices of degree large enough to be branch vertices of this TKR. And now the assumption is that the min degree of G is not just at least 3, but is at least R minus 1. But given that, you get a TKR as long as your girth is big enough. So that's quite something. But the really fantastic theorem comes now. This is due to Daniela Kuhn and Derek Osthus. Daniela was my first student here at Hamburg. So she's now a famous extremal graph theorist in Birmingham with her husband, Derek Osthus. And they proved that you can get that for every R by the same constant on the girth. So once more, there exists a universal constant, little g, such that for every R, every graph of girth at least g and min degree at least R minus 1 contains a TKR. Pretty unbelievable theorem. But they're not known for making mistakes, so that is indeed a theorem. Okay, so let's get back to forcing TKR, not by making the girth large, but by giving our graph enough edges. And at the end of the day, we want to prove that constant times R squared times n edges, or average degree at least constant times R squared, force a TKR subgraph or a topological KR minor. That's our goal. And I'll prove that to you today, assuming another theorem about linking vertices. That's some connectivity statement, but linking vertices, that will take 2 lectures to prove, and I'll do that next week. So that linking theorem is a theorem due to Paul Wallen, a student of Robin Thomas, and he did that in his PhD, pretty amazing. So that will be next week, and today let's just look at this problem of how to force a topological KR minor by assuming that the average degree is large enough in terms of R, pre-Wallen. Okay, so in graph theory 1, I showed you that there exists such a function of R that ensures that. And the average degree we needed there was something like 2 to the Erdös-2. And the reason for that bound was that we did induction on the number of edges of this KR that we wanted to, a subdivision of which we wanted to appear in our graph. And we added one subdivided edge at a time, and every time we did that, we lost a factor of 2. So we got to a bound, a guarantee of having a TKR subgraph of 2 to the power of however many subdivided edges we needed, namely Erdös-2. So that's the state of the art for this class, and we want to improve 2 to the Erdös-2 to R squared. Okay, so how can we improve it? Rather than add these subdivided edges one at a time, which gives us Erdös-2 steps, and maybe we lose a factor of 2 every time. Rather than doing that, the approach will be different. We'll pick our vertices, which are going to be our branch vertices, in our given graph, which we assume has large average degree, or maybe equivalently you can assume it has large min degree, right? Because you only lose a factor of 2 by going from having a certain average degree to a subgraph of a certain min degree. And similarly, you can proceed to a subgraph of some required connectivity, and you lose from the average degree to the connectivity a factor of 4. Both these things are in the first chapter. So we'll pick some vertices, it doesn't matter which, and for each of them, we choose R minus 1 neighbors. So R vertices here, each of them has R minus 1 neighbors. And the idea now is to link them all up to give us a subdivided KR with these chosen vertices as branch vertices. Right, so we have to link up these neighbors. There are enough of them somehow in pairs. So as to, not somehow, but in some very specific way, so that these paths added to the little stars between them form a TKR together with these stars. So that's a complicated assignment that tells us to find these paths. And so we want the set X of all these neighbors together to be what is called linked. What does linked mean? A set is linked if you can pick any 2 disjoint subsets of the same size and prescribe a pairing. Say you want to link this vertex to that, and this vertex to that, and this vertex to this, and so on. And no matter how you choose these subsets, and no matter how you choose the pairing, this pairing will exist, a path pairing. And it will exist by paths that run entirely outside X. So once more, a set X of vertices in a graph is linked if for every two disjoint subsets of its vertices, equally sized, and every pairing of the elements of these two subsets, we can find a path system entirely outside X, except for the ends of these paths, realizing this assignment. Disjoint paths. That would be really nice if we had such a statement about this X. This X is given to us, right? We just blindly chose these R vertices, then we took R minus 1 neighbors of each of them blindly, and now we're landed with this yellow set X, and we come home and cry a little bit and say, well, could I have X to be linked, please? All right, so let's see whether we can get that. And so more generally, or no, more specifically, the graph G itself is K-linked if for every choice of K vertices on the left, call them on the left, and K other vertices, call them on the right, there exists for every pairing of these two a path system realizing this pair, a system of disjoint paths in G. Right? For every K set, every other K set disjoint from it, every sort of pairing of these vertices with those vertices, there exists disjoint paths realizing this pairing. And if that's true for in G, for every choice of these vertices and every pairing, then G is called K-linked. So this is clearly a strengthening of K-connectedness, right? K-connected, if you're K-connected, then Menger ensures that for every two such sets, you have some system of K-disjoint paths from one to the other, but you cannot choose how to pair them. And the notion of K-linked is stronger than that, so it's stronger than K-connected because it allows you to choose the pairing. Okay, so out of general interest, it's natural to ask whether some function of K ensures this if the graph is that function of K connected. Right, this is a strengthening of connectivity, of connected. So if we make the graph f of K connected for some function f, will it be K-linked? Why is that relevant to us? Because in our attempt at constructing our TKR, we're assuming that we have large min degree. Well, then we have a subgraph that's highly connected. And so we only lose from the, average degree to connectedness, we lose a factor of 4 only. So we have a subgraph that's highly connected, and if that's sufficiently connected to be even K-linked, or if you like, have a subgraph that's K-linked, that's not an avenue we're going to pursue, but that would be enough for this particular application, then we'd be in business here. Okay, but it is a completely natural question to ask about this function f with a property that every f of k, that for every k and for every g, if g is f of k connected, then it itself is k-linked. So that's a natural question. And I want to address this question now, completely independently of the intended application to TKR. finding TKRs. Okay, questions at this point? So the question we're going to pursue now for the next 15 minutes is which function of k connected implies k-linked? Okay. Okay, so let me show you some such function. This function and this proof that I'm going to show you is due to Heinz Jung. He was one of those 3 students of Wagner's. And it was independently proved in the same year, I think, by Larman-Mani in the UK. And so the proof idea is as follows. We would like k vertices to be linked to k other vertices. So let's call these T1 to Tk, and these are called S1 to Sk. And the idea to maybe achieve that is to hope to find somewhere deep inside the graph a kind of switchboard, a dense subgraph. We're not trying to prove that the entire graph is dense, but we want to find a dense subgraph so that we can then link the vertices on the left, and the vertices on the right to this subgraph. And then because this is dense, we can somehow find on this switchboard the pairing that we have prescribed. So for example, if this was a complete graph on 2k vertices, that would work, right? K paths to it, k paths from here to it are, well, yeah, 2k paths from the union of those to the complete graph on 2k vertices by Menger. They arrive anywhere. We can't control that. But no matter where they arrive, we then have the required edges to do the pairing. So if this was a k to k, that would be lovely. Of course, we can't find that because we're in sparse graph theory here. So maybe what if we find a subdivided k to k? Well, that would still work if our landing vertex is here, and we're all branch vertices of this. If it just so happened that our 2k paths that Menger gives us from the Si and the Ti to this central thing, if those happen to land on branch vertices, then we could do the clearing, the switching. inside that T 2K, TK 2K. There's a problem, and the problem is that they don't have to land on branch vertices. Right? So if this one here, well, let me put it this way. We ask Menger to give us disjoint paths from the SI and the TK and the TJ to the set U of branch vertices. We don't ask it to give us paths anywhere to these, because if a path just lands on a subdivided edge, that's no good. Right? We want to. No. So we ask for paths to the set U of branch vertices. But now it can happen that on the way to a branch vertex in U, this path crosses one or many of these subdivided edges of our TK2K. And this subdivided edges it crosses, maybe it goes from here to there, that might be needed for our switching, right? I mean, not if it goes up there, but if it goes up here, we want to pair SK with TK, so we'll want a path from here to there, and maybe this path is hit by this path from our path system. Call these paths PK, right? All the paths from the SI and from the TJ to U, call that path system curly PK. So that's a problem. And there's a really nice trick that deals with that problem. And the trick is that we choose these paths in curly PK in a particular way. Or I just called it curly P. Never mind, curly P. Choose them in such a way so their paths from the SI and TJ to big U, to the branch vertices, that have as few as possible edges outside this K. So once more, we choose these paths so that they use edges of this subdivided K to K whenever they can. Or more precisely, we minimize in the choice of this path system. Menger tells us there exists some path system. We choose one that minimizes the number of edges outside this that it uses. And that's something one can just do. Whether or not it helps is another matter, and it does help. So let me show you why it helps. For a start, we need to change the 2K here to 3. So K is a subdivided K 3K. So we have some more branch vertices that we didn't hit. We hit only 2K of the branch vertices that we have, and we have 3K many now. Okay, so why does choosing P in this particular way help? We're going to use these for our switching purposes too, so let me just draw an example. Where this path here, P3 say, hits the subdivided edge from U2 to the end point of P2, which is another element of big U. Right, so if this P3 hits that path here, then this path cannot be used for switching purposes, which we might want to do. So it's even worse if this path here hits a path between elements of U that are not the extra elements, like this one here, which I drew earlier, but I want to work with this picture now, so let me draw this example like this now. Okay, now we have a choice of curly P as saying that the paths use as few edges outside K as they can. Now, give this vertex, let this vertex be let's call that V2. More generally, let's look at the subdivided edges between the UI, the extra vertices here, to the end vertex of Pi. So from UI, in this case U2, we look at the subdivided edge in K, in this TK, 3K, that goes to the element of big U, to that branch vertex, which is the end point of P2, or Pi in general. Okay, so, and let V2 be the first vertex of this subdivided edge. This subdivided edge is called Li, so this would be L2. Let Vi be the first vertex of this subdivided edge that lies on any Pj, any of them, for example, here on P3. But the point is that these vertices here don't lie on any P. Now, what can we say about P3? This path that gets hit here, let me just call it P. This path that gets hit had an option. When it got, you can't see yellow, can you? So let me use orange. When this path got to that vertex, well, it still had some way to travel, but when it got here, it had the option of turning off along L2, or Li more generally, because this portion of the subdivided edge L2 does not hit any other P, right, by the minimality of V2. V2 was the first vertex on the subdivided edge, coming from U2 to the endpoint of P2 that lies on any of these P's. So these vertices don't lie on any of those P's. So when our P got to that vertex, one option was to continue to U2. Right? U2 hasn't been used by the path system. That's why that's why we needed 3K. So U2 hasn't been used, but it could have been used. So this path P had this option of turning off and going to U2? Well, it didn't. The reason it didn't must be that after this vertex, it did what it would have done here, namely not use any other edge outside K. But how can it not use any other edge outside K if it continues like this? There's only one answer. It must have continued like this. Like this is a vertex on this subdivided K, 3K, and it's hit it, and there's no other way to continue among these edges than going to this branch vertex or going to that branch vertex. There's the only two ways to continue only along edges of this. So since it didn't continue here, it must have continued there. So in fact, our P is P2. We have proved that this P ends up at what is this vertex? This is, by definition, the end vertex of P2, because L2 is defined as the subdivided edge from U2 to the end vertex of P2. So this P here is, in fact, P2. And now, maybe I can draw this picture slightly differently, and then it becomes clearer. In general, from SI, we travel along PI, and then go to some branch vertex in big U, as in this picture. And now, instead of doing that, and here from Ti, we reach K and then travel along a subdivided edge to some element of U. And this point down here, that's the yellow vertex U3, UI. Right, so I'm just repeating this picture, magnifying this situation here, over here. The definitions are exactly the same as there. We found that Pi here, I was 2, travels to V2, which is the first vertex on the path from U2 to the end vertex of P2, or from UI to the end vertex of UI. Maybe it is the end vertex of UI without finding anything. Maybe it hits this edge first, and then if it hits this subdivided edge, it then turns off and follows it to its end vertex. And now we can do the switching. We can instead, we can follow from SI until we hit LI and travel to UI, then travel along this corresponding subdivided edge from UI to the end vertex of QI, which so this would be QI, and if this is LI, then this is called MI, so we can travel over there and then follow this path qi back to ti. So we can use that, do that for every I. And these switched paths don't get in the way with each other because these little bits that are new, previously the orange paths didn't get away in each other's way because by Menger were disjoint. Now, we added some other little bits, but every other vertex that we added was added only to one particular pair. Right? Because all these vertices here, by the minimality of V2 on this subdivided edge, all these vertices here lie outside the orange paths in curly P, and they also lie outside any other such switched paths because the other ones go to uj for j not equal to I. Right? So these new things are unique to their I, so we get another path system, this time joining the correct pairs, every Si to every Ti, as a result. Okay.